have the third lecture of the lecture series, Introduction to K-stability and Finite Generation. And the speaker will be Ziquan Zhuang.
Okay, so thanks, Chenyang, for the introduction. All right, so today I want to continue with the lectures from the previous week. So in the last week, so Yuchen introduced the definition of K-stability and talk about this concept. And then on Friday, I mentioned a few conjectures, and at the end of that day, I think we essentially reduced everything to the so-called finite generation conjecture. So this week we want to at least sketch some ideas that goes behind the proof of this statement. So let me first record the statement. Okay, so the theorem is the following. So this is joined with Chenyang and Yuchen. So it says that if I have a Fano variety, X, and the so-called delta invariant is at most 1, and it's computed by some valuation. So it's equal to A over S for some valuation V, and this is at most 1. Then this associated graded algebra is finitely generated. Right, so that's the statement. And actually, in our proof, you can relax this assumption to less than n plus 1 over n, where n is the dimension. But I'm not pretty sure whether we have time to cover that. So, but I mean, for most of the applications, less than or equal to 1 is good enough. Okay, so let me just state things like this for the moment. Okay, so let me maybe first record some of these notions for you. So for instance, so what's this graded algebra? So here R is just the section ring of the Fano variety. Okay, so then for my valuation V, I get the filtration of this section ring. So F lambda is given by the sections whose value is at least lambda. And then this graded algebra is given by taking the direct sum of all the graded quotients of this filtration. Okay, so this graded algebra is given by taking the sum over all m and lambda of the graded quotients of this filtration. So the statement is that if the valuation comes from the minimizer of this delta invariant, then this graded algebra is finitely generated. And last time we see that this finite generation is closely related to having the optimal degeneration of the Fano variety. Okay, so let me also recall from last week that when I have a valuation that computes the delta invariant and the delta invariant is at most 1, then this valuation V is always a log canonical place of complement. So that was the result by Chenyang, and so Harold, Yuchen, and Chenyang. So this V is always a log canonical place of complement in our setting. So in other words, you can always find an effective divisor D that's Q-linear equivalent to the minus the anti-canonical class, such that the pair X comma D is log canonical. And when you look at the log discrepancy of this pair along the valuation V, you get 0. Okay, so that's the meaning of this sentence. And so let me remark here also that all right, so why is this called the higher rank finite generation conjecture, right? So when the valuation has rational rank 1, so that's when it's a divisorial valuation. So in other words, it comes from an actual divisor on some birational model. So when this valuation is divisorial, this finite generation result is basically a consequence of BSHM. So Burkhardt, Cassini, Hagen-McKinnon. So because when this divisorial log canonical place of complement, then so in this case, let me first write it down. So BCHM gives you the finite generation we want. So the reason is that when it's a divisorial log canonical place of complement, you can extract this divisor on the blow up, on the PLT blow up, and such that the total space remains of Fano type. And because it's a Fano type BCHM, so this is so the consequence of BCHM. So because it's a Fano type, when you take, for instance, any Cox ring construction, you get something that's finitely generated. And this graded ring is basically a quotient of certain Cox ring. So it remains finitely generated. Okay, so that's the remark. So the higher rank finite generation conjecture basically asks for the same, like a similar statement for evaluation of higher rational rank. And there things starts to become a little bit tricky because so it's not true that the same statement will hold for higher rank valuations. So I'll explain this shortly. So the statement will fail if V is of higher rank. All right, so at the end of the day, certainly we want to replace this delta condition by something that's more birational geometric. So here, being an LC place of complement looks very natural, but it's unfortunate that we still need something else when the valuation is of higher rank. Okay, so that's the remark I want to make here. Let me finish recalling some of the materials. So since we have an LC place of complement, this valuation, again, as we mentioned last week, is quasi-monomial. So that means I can find a log resolution together with a simple normal crossing divisor on my resolution. Okay, so Y is a resolution. This is a simple normal crossing divisor, and I can choose a bunch of weights. So these are positive numbers, such that so these weights, they are linearly dependent over the rationals, such that my valuation V is a monomial valuation along this this simple normal crossing stratum. Okay, so roughly speaking, it's the weighted blow up along these components with weights alpha 1 through alpha. Okay? And you can always choose a model such that the weights, they are linearly dependent over the rational numbers. Right? So this R is basically the rational rank. So maybe for convenience, I will call the set of these valuations. So I denote the set of valuations like this. So this notation here, this QM stands for quasi-monomial valuations that becomes monomial on this resolution Y and with respect to this simple normal crossing divisor. Okay, so here is this sum. Okay, so this is just a notation. And if you choose different weights, then you still get a valuation in this set. Okay, so the subscript here will stand for the weight. Okay, so I think this is all from the previous week. So then I said earlier that as long as you choose a valuation of higher rank that remains in log canonical place of complement, this finite generation can fail. So let me first explain why is that, and then we'll see what's the subtlety. Okay, so this follows from a proposition by, I guess, some part is in the paper by Shili and Chenyang, and another part is in the paper of Chenyang. So the statement is as follows. So it basically gives some obstruction to this finite generation. So let's assume that this graded algebra is finitely generated, then the following would hold. So the first one is that so now this valuation comes from such a quasi-monomial valuation, so I can perturb the weight. The first statement is that if I perturb the weight, I will get the same graded algebra. Okay, so this graded algebra will be isomorphic to the associated graded algebra, so V beta. If I perturb my beta, my weight sufficiently small. Okay, so if I have a very small perturbation of the weights, I get the same graded algebra. And secondly, so for any weights, I can look at the associated Asym Variant or the expected vanishing order of the corresponding quasi-monomial valuation. Okay, so the second part is that this function has to be linear in the neighborhood of the original weight alpha. Okay, so that's the statement. Is everything okay so far? So let me very briefly explain what's the reason for this. So I think there's something that's better figure out when you look at the details, but at least let me explain why something like this would be true. Okay, so for the first one, the point is that, all right, so if we assume that this graded algebra is finitely generated, then you can pick a finite set of generators, right? So you can choose generators. So you put a bar of it. So these are generators of this graded algebra. And so there will be some relations among them. And because it's finite generated, you only need finitely managed generators to determine this algebra, right? So there will also be a bunch of relations. So what they show is that so now I can lift this generators to R. Okay, so maybe the lift is called F1. So I drop the bar. So what they show is that, so now I can restrict these generators to my other graded ring. So what they show is that, so if you restrict this lift, so they will restrict to generators of this graded algebra if you perturb the weights only a little bit. And also the relations also restrict to relations of the restriction of this F. So this will restrict to relations. Okay, so that's how you show that in this graded algebras they are isomorphic. Okay, so that's the rough idea. And secondly, so now if I look at the value of these generators, okay, so my V alpha of these generators, so by definition, so this value is given by, all right, so you write down the F, these functions into a Taylor expansion, and then you choose the weights of the monomials that appeared in this expansion, you choose the smallest one. Okay, so so at the end of the day, this value will be a combination of the weights alpha I. And because I assume that these weights, they are linearly independent, and there's a unique monomial that achieves this weight. Okay, so then if I perturb my weight a little bit and look at the value of the same function using my new weights, then the same monomial will account for this smallest weight. Okay, if the perturbation is small enough. Okay, so I'll get the same weights for this value, except so the same linear combination, but I just have to change the weights from alpha to beta. Now, what's the Asym variant? So, so this Asym variant of evaluation, no, it's the expected vanishing order. So in some sense, it's the average. In some sense, it's the average weight of this graded algebra. Okay, so now if the generators, if you look at the weights of the generators, you are changing alpha to beta, then the same holds for any element in this graded algebra. So if the Asym variant of V alpha is some linear combination of these weights, I mean, it has to be because everything here is a linear combination of the weights. Then as you change your weights from alpha to beta, you will still get the same linear combination, except that you are changing alpha to beta. Okay, so that's how you know things will become linear in the neighborhood of the original weight alpha. Okay, so that's the rough reason why we have these two abstractions. Okay, making sense?
Excuse me, is it possible to say something a little bit more about one? I mean, where this trick can't work completely generally.
So, right, so I mean, so for instance, you also need this perturbation in one, so you have to make sure that the weights, they also change linearly. And then so this relation means that so there are some combination of this alpha such that the monomial of smallest weights gets eliminated. So then it becomes something of larger weights. So you perturb the weights a little bit such that the bigger monomial remains there. Okay, so that's roughly the reason. So that's only the two conditions that you have to ensure.
So you're not using that this is like an anti-canonical ring. This would work more generally, or?
Yeah, I think so.
Okay.
Yeah. Yeah, this is just some statement about graded algebras.
All right, thank you.
Okay, so all right, so now assuming these two abstractions, so let's see some example and see and check where the finite generation would hold in general, right? So okay, so let's take one of the simplest example where my Fano variety is just P2, and so I want the log canonical place of a complement. So let's choose the nodal cubic as the complement of the alpha curve. So so its log canonical places are exactly the weighted blobs along. So analytically is the weighted blob along these two analytic branches. Okay, so I have to choose different weights on the two branches. I mean, certain weights on the two branches. Okay, so let me call V sub t. So the weighted blob with weights equal to 1 on one branch and equal to t on the other branch. Okay, so all right, so let me just leave it like this. I guess the notation is explains itself. Okay, so so then the previous proposition will imply that if I have finite generation of the weighted ring associated to this thing, this valuation, then the Asym variant has to be linear in T. So if T is irrational, okay, so then Asym variant has to be linear in the neighborhood of that number. Now this is just P2, and you have a weighted blow-up. So everything can be computed very explicitly. So I think Kanto Fujita already computed this number in some sense. Okay, so so he showed that in this case, the Asym variant of my P2 of this weighted blow-up is equal to the following expression. So it's 3t over the pseudo-effective threshold plus the pseudo-effective threshold over 3. Okay, so I'm not going to repeat his calculation, but that's the final answer. Where where this capital T is the pseudo-effective threshold. So in other words, is the so the vanishing order, the largest vanishing order of effective divisors that are Q-linearly equivalent to minus K. Okay, so now if you look at this expression, you might think, all right, so how can this be linear, right? So you have something in the denominator and the numerator at the same time. And in fact, it's not. So in this pseudo-effective threshold, one of the natural candidates for this pseudo-effective threshold, I mean, the candidate for this divisor D is exactly this nodal cubic. Is there something in the chat? Oh, yes, sorry. There's a suit here. Yeah, it's the largest vanishing order. Thanks. Yes.
So quick question.
Yes.
So what's the difference between this nodal rational and like a two line? I mean, I think a two line is going to be linear, right?
Yes. So
okay,
yes,
yeah.
I mean,
so if it's a two line,
so right. So I mean, it's not entirely impossible that this whole expression becomes linear. So for instance, if the pseudo-effective threshold is linear in T, then it becomes linear. I mean, it's a multiple of T, then it becomes linear. So there are some complement where it becomes linear.
Yeah.
Especially
if T is it's just equal to little t, yeah. It's just equal to little t, yeah.
Yeah. However, if you choose the nodal cubic, then the most natural candidate for this divisor that computes the pseudo-effective is this nodal cubic. And then there the weight becomes 1 plus T. Okay, so in fact, you can show that if this weight is sufficiently small or it's sufficiently large, then the pseudo-effective threshold is exactly computed by this nodal cubic, and that's 1 plus T. Okay, so this is not linear, and sorry, so the Asym variant is not linear. So that means even for this complement, we get log canonical places that doesn't have a finitely generated graded algebra.
So yeah, so what about a double line? I mean, other than a double line, just two line x, y equal to 0.
Right. So I mean, for two lines, you always get like a toric blow up. So for toric blow up, I mean, one of the line doesn't account for the pseudo-effective threshold. You are only using one of the components.
I see.
And similarly, if you have like one line and the conic, I think in the end you always get one component or some single curve that accounts for the pseudo-effective, but it's not the nonlinear curve, like not the conic.
I see. Thank you.
Yeah. So the upshot is that if you construct this complement carefully, then you will get some non-finite generation. Okay, so now it seems that we might be in some trouble, right? So because in general, even if you have a log canonical place of a complement, you don't always get finite generation. So maybe what might make you worry even more is that, so maybe there are more obstructions to finite generation, right? So we found 2 so far. So the good news is that that's the only thing. Okay, so now let me state perhaps the first technical result, the theorem, is that so now if I assume the valuation is a log canonical place of complement, as always in the lecture, then this graded algebra is finitely generated if and only if this Asym variant function is linear. Okay, so that's the only obstruction we are going to get. So before I say anything about the details. So let me first make some general remark, maybe. And because I'm pretty sure some of you might be curious how something like this will be important in the actual proof of finite generation later, because this is not something that's very easy to use to verify in some sense. Okay, so all right, so the first remark is that, so actually this might seem to be a coincidence, at least for me. So it seems that actually every time you prove some finite generation, there will be some linear function involved. Okay, so I think in BCHM, when they prove the finite generation of certain section rings, basically, or joint rings, section rings of a joint type. So for instance, like the canonical or maybe plus a divisor. So there, of course, you have a big induction involved. But at some point in the induction, you have to feed in this base locus function. Okay, so at some point you have to show that this is linear, and you feed that into the induction, and at the end you get a finite generation. So so here we want this graded algebra to be finitely generated. So at some point you have to feed in a linear function, and it turns out this Asym Variant function is the right choice. Okay, so now of course in general you don't get this linearity for free. So in either cases you need some birational input. So I think in BCHN, this birational input is given by the Haken-McKernan's extension theorem. So in our example, so this will come from something very different. So at the I guess maybe next time, or hopefully at the end of today, we introduce the notion of special complement. So the statement will say something like, so if you assume a little bit stronger that this valuation is a log canonical place of a special complement, okay, so put special here, then this Asym variant is actually linear. Okay, so that's the birational input to guarantee this finite generation. And of course, in this area, we already need BCHN. Okay, so basically induction is all taken care of by BCHN. So so what this special means, so let me say very briefly. So just as the name suggests, so if you have a log canonical place of complement, it induces a degeneration to something log canonical. And so a special complement is a complement where basically the log canonical places induces a degeneration to something KLT. So I want the degenerations to be special instead of only weakly special. Okay, so roughly, so this means all degenerations, all induced degenerations are special. Okay, I need more space. Okay, so that's what it means roughly. All right, so that's a remark on the general structure of what we are going to do. Okay, so so then maybe let me focus on this statement for the moment. Right, so so I think you have seen one of the implications. The reverse direction is hidden in a curious property of the convexity of this Asym variant. Okay, so I guess if you look at the base, I mean, usually when you want something like this to work, you want the corresponding function to be convex or concave, depending on how you define them. So for base locus, that's pretty much clear. So if you have two line bundles, the base locus of their sum is contained in the sum of their base locus. So however, for Asym variant, it's not entirely clear. Okay, so so actually, eventually the proof is hidden in this convexity. Okay, so here's the lemma that So basically this function, okay, so I think I should put v beta here. So if you, so the function that assigns the weight to the Asym variant of the corresponding quasi-monomial variation. So this is, let's see, concave. So this is a concave function. So in other words, so if I choose two different weights, I'm going to get, okay, so this is what I mean by concave. Maybe some of you will object, but okay, so if I take linear combination of the weights and look at the Asym variant of the corresponding quasi-monomial variation, so this will be greater than or equal to the linear combination of the Asym variant at the two ends. Okay, so this is what I mean. Okay, so so as I said earlier, the convexity of this is not so clear in our setting. So actually, the proof requires a little trick. So this is related to the notion of compatible divisors. So let me introduce that first. So so this was introduced in an earlier work, in an earlier joint work with Hamid. So there we were studying like K-stability of explicit examples. But turns out this notion is also useful in other settings as well. So let me give the definition. So maybe let me first recall what's a basis step divisor from Yuchen's talk last Tuesday. So let me recall that the basis type divisor, maybe m basis type divisor. So m is an integer of my Fano variety is of the following form. So I take a sum of the zero locus of a basis of the plural and canonical sections, and then you average it and rescale so that it's clearly indeed equivalent to minus k. Okay, so so this SI so let me just write it down. So this SI they are bases of the plural and canonical sections. Okay, so now I can define compatible divisors. So I'm going to say that this basis step divisor is compatible with the filtration, with a fixed filtration F on this section rings, on this global sections. So I'm saying this is compatible if every filter subspace is spanned by some of the sections SI. So most typically, this filtration will be the filtration that's induced by a valuation. And so, so forgetting the previous context first, so why is this definition useful? Okay, so so here's the remark. So there are different ways to define this Asym variant, but so I guess last week we used the integral, the formula that comes from the integral of volumes. But another way to define this formula is to use the take a limit. So I can first define the Asym variant at the finite level. So I have a value. If I have a valuation v, I can define this Sm of v as the largest vanishing order of m basis type divisors like this. And then it turns out that as you take the limit as m goes to infinity, you will get the Asym variant that was introduced last week. Now, if you want to, so the supremum, since we are at the finite level, the supremum is a maximum. And it turns out that if you want a basis type divisor that achieves this maximum, what you need is exactly a divisor that's compatible with the filtration that's induced by this valuation. Okay, so let me write that down. So the supremum is achieved by this basis type divisor D exactly when this basis type divisor is compatible with the induced filtration V. Right. So after all, if you want to choose a basis that maximizes the vanishing order, you have to enumerate all these filter subspaces. Okay, so I hope that's more or less clear. Okay, so that's why this comparative divisor will be useful if you want to prove something that's related to the Asym variant. Okay, so now with this tool, I can talk about this lemma, so the concavity of the Asym variant. So the plan is now more or less clear. So okay, so let me just write concavity of S. Okay, so the plan is here. So all right, so now since I already said this Asym variant is a limit, so I just have to show that this Asym variant, they at least on the finite level, they are also concave. Okay, so it suffices to look at the corresponding concavity at finite level. Okay, so I'm just copying the same inequality by replacing S by Sm. All right, so and now I know that if I'm going to compute this Asym variant using some divisor, I'd better choose a compatible divisor, according to my previous remark. And I don't want to have too many divisors involved, so so let's choose a divisor D that's M basis type, and also compatible with both valuation that's involved here, so V alpha and V beta. Okay. So then if I look at the right-hand side, I'm just taking the vanishing order of this divisor D. Okay, so then the right-hand side becomes V alpha of D, and then 1 plus T of V beta of D. While on the left-hand side, I know it's at least the value of D along this intermediate valuation. Okay, so we want something like this. So in fact, so this is always true for any divisor D, because again, so when I take the value of this quasi-monomial valuations, I'm looking at the smallest weights of monomials that occurs in the Taylor expansion. But so now I'm taking linear combination of the weights. But if I know that when I look at the weight with respect to alpha, it's at least this. And when I respect to the weights of beta, the corresponding weights is at least this. So then for the linear combinations, the weights of the monomials will be at least this linear combination. Okay, so in fact, this last comparison is always true. And why can I always choose the basis type divisors like this? Well, so that's linear algebra effect. So if you have if you choose any two filtrations on a vector space, you can always choose a basis that's compatible with both. Okay, so we are done. And now, so this is just the concavity. But now if you have linearity of the Asym variant, so then essentially you want equal here. So that would tell you that basically, so this is also equal. So in some sense, the intermediate, so for this intermediate valuation, the corresponding filtration is roughly determined by the filtration from alpha and from beta. Okay, so if you choose a weight, it's always in the convex hull of some rational weights. And we know that the filtration in the middle is basically determined by the filtrations on those rational weights that determines this convex hull. But according to BCHN, if you choose rational weights, you always get something that's finitely generated. So you have a filtration that's determined by a bunch of finitely generated objects. So that's how you conclude that it's in general finitely generated. So that's the proof. I won't write that now because it's more technical, but that's the idea. Okay, so then for the theorem that Asym variant is linear implies finite generation, you study the equality case in the proof I just presented. So we study equality and show that there's filtration in the middle, V middle is determined by the filtration at the vertex. Okay, so and these are rational, so they are finitely generated. Okay, so that's the rough idea. Okay, this is making sense. I don't know if I'm going too fast. All right, so now at the end we have a criterion at least for finite generation. Although it's not birational geometric, we have some criteria. So the criterion is that if I want finite generation and I really know it's a log canonical place of complement, then I have to find some way to verify that this Asym variant is a linear function. And we want some birational geometric input here. Now, if you go back to the two obstructions that I used earlier, you might notice that somehow the first obstruction gets lost in this process. So only need a second one. So you might want to absorb this first obstruction into the criterion as well. And in fact, you can do that. So, so now let me state the full version of the theorem. So here I'm only stating part of the theorem, basically. So, all right, so let me state the full version of the theorem that incorporates the other obstruction. Okay, so that's, let me call it theorem A. Okay, so at some point there will be another theorem for finite generation. All right, so again, let's assume that the valuation V is a non-canonical place of complement. And so I adopt the previous notation. So V is going to be V alpha on some log resolution and some simple normal crossing divisor. Okay, so it's a quadimonomial valuation like this. So then the following are equivalent. So first, this graded algebra is finitely generated. Second, the Asym variant function is linear in the neighborhood of alpha. Okay, so I forgot to write. So it's here, and the alphas, they are linearly independent. That's always important. Okay, so then the following are equivalent. All right, so let me finish the sentence very well. Okay, so the Asym Variant function associated to a weight to the Asym Variant of the quotient monomial valuation. This is linear in the neighborhood of V alpha. And third, so ideally you might want to write this graded algebra stay the same when you perturb the weight. But actually you can weaken this condition. So the only thing you need is that so when you look at this set of this graded algebras where so beta now is rational, so it comes from, so it gives you a divisorial valuation, and it's sufficiently close to the weight alpha. So okay, so since I assume that this is everything here is a log canonical place of complement, so this graded algebra when you take the approach. Okay, so I forgot to take the approach. So that will give you a log of, no, at least a Fano variety with semi-log canonical singularity. So that's the third criterion. So the last criterion is that, so this set of Fano variety is bounded. You don't need to assume that they are all the same. You just need to assume that they are bounded. And of course, if you know finite generation, they are all the same. And this is something that we would like to study in birational geometry. Okay, so it's about in this question. All right, so I think I already explained why 1 implies 3 and why 2 implies 1. So I only have to tell you why 3 implies 2. Okay, so here for the last arrow is another elementary fact actually. So so the fact is that right, so now we already know this is a convex function. So if I have a convex function, sorry, concave function, it doesn't matter. So you have a concave function that sends rational numbers to rational numbers and keep the denominator, then it's linear. Okay, so so I call it S. So if I take rational numbers of this denominator to rational numbers of the same denominator, then well, maybe I should be more careful. So then this S is linear, piecewise linear. Maybe you should write so it's piecewise linear. Sorry, piecewise linear with a rational coefficient. Okay, so this uses some Diophant-time approximation, but it's not too hard. But maybe it's easier if you think about some example, right? So if your S takes x to x squared, so sorry, minus x squared. Okay, so there's something that takes rational numbers to rational numbers, but you raise the denominator. Okay, so usually when you have something that's not linear, then you have to raise the denominator. Okay, so if the denominator doesn't get increased, then it's linear. Okay, so now if you have boundedness, well, so then this Asym variant so comes from 2 parts. So first you have to eliminate the denominator of this variation to get an actual divisor. So we are choosing integer weights and do the weighted block. Now, so I can always compute this Asym variant by taking the average weight on this on this degeneration. So taking the graded algebra and the product of that. But this is a bounded set of Fano varieties. So if you take a bounded family of Fano varieties, this denominator, there is a universal bound. So if you clear that denominator, then then this Asym variant will satisfy this condition. Right? So boundedness guarantees that it's just like when you take volumes of a divisor in the bounded family, then this volume, I mean, they can be rational, they can have a denominator, but that denominator is bounded. So that's the advantage of having a bounded set. Okay, so then this boundedness from 3 is going to tell me that, so at least when I take Asym variant and I clear the denominator, let me just write. We imply that this Asym variant function satisfies the property that I used above. Right, so if you multiply it by some universal integer in the front, then it's going to take rational numbers to rational numbers and without increasing the denominator. Okay, so that's the idea. Okay, so eventually we finally reduce the finite generation problem to something we might be able to treat in birational geometry, which is related to some boundedness. And this pros, they are just some Fano varieties. The only problem is that these Fano varieties, they can have very bad singularity because I only assume that the complement is arbitrary. So a priori you can get some Fano variety with log canonical or maybe semi-log canonical singularity. And we certainly want to avoid that. I mean, we do have some boundedness theorems for Fano varieties, for instance, right? So for instance, the one we are going to use later on is this theorem by Chenyang, which is based on BAB, Berkas BAB proof. But I mean, at the end, later on, we also have a proof that reduces only to the Batyrev's conjecture, proved by Chenyang Xu. So anyway, so the statement is that if I look at the set of Fano varieties, KLT Fano varieties, of dimension n, such that the alpha invariant has a lower bound, and the volume also has a lower bound. So then this set is bounded. So here, this alpha, so this lower bound, they are my chosen constant, greater than 0, of course. Okay, so we do have some boundedness property for Fano varieties, except we have to assume that they are KLT. Okay, so this is where we want to introduce a different notion of complement. So we want to have some special type of complement, such that when you look at this associated degenerations, what you get is actually a Fano variety with KLT singularities. And so that at least we have some hope of applying boundedness results that we already have in birational geometry. So so let me state, I think I don't have too much time to define maybe, so I'll leave that to Richard next time. So let me at least state the next criterion, which will be very useful later on. Okay, so now the final criterion will be this. So now I have a quasi-monomial valuation. Then the following are equivalent. So first, this graded algebra, so X is Fano as always. So this graded algebra is finitely generated. And so if you look at the corresponding approach, you get a KLT Fano variety. Then this is equivalent to saying that this valuation V is a so-called monomial log canonical place. I mean, this is what we call it, of a special complement. Okay, so as I said, so the special complement is a concrete definition that allows you that guarantees that every associated degeneration is special. So it has KLT singularity. So I guess maybe I'll just leave the statement like this, and then Yuchen will continue next time. So at least I think he will tell you what's special. What's a special complement? Right, so I think I'll stop here.
Okay, thank you very much. So any further question?
So can I ask? So as S is local linear around finite generation valuation, so can we say anything about the maximal linear domain in a fixed complex?
I'm not sure. Yeah, so there's this thing that usually comes from Diophantine approximation. So it's hard to say how big you can get.
So do we expect it to be a polytope?
So I think it's reasonable to expect that it's locally piecewise linear if you use a special complement. But in general, it's hard to say. So so for instance, so earlier when I used this P2 and the nodal cubic, so the dual complex here, it's a circle. So basically the weight can go from 0 to infinity, but when it's 0 infinity, you get this nodal cubic. Then so there I said, if you look at the neighborhood of this 0 and infinity, then you don't get S linear. But there are certain regions when S becomes linear. And actually the regions, they are smaller and smaller and smaller. And so there is a certain point where it's not locally linear. But if you just move a little bit away from it, then it becomes linear. Yeah, so it seems to suggest that if you look at the dual complex, there is some special region where things are locally linear, a little bit like the Kohn theorem, actually. So there are certain regions of the dual complex where this Asym Variant function seems to be locally linear, but there are also regions where it behaves very badly. Yeah, and
Okay,
I don't think I have anything I can say about how far you can extend the linear region. But my feeling is that in some sense it looks a little bit like Kohn theorem. I don't know how, but it looks a little bit like it.
Okay, thanks. Okay.
Any other question? So if no, let's thank you again. And let me remind you in chat, I think Carl just posted the link of gather time. Okay, let's thank you again.
Okay, thank you.
And I think we'll review them on Thursday.